So something that's really common is we don't know the amounts at equilibrium, but we know how much we started with, and then we want to figure out how much we'll have at equilibrium. And you use what's called an ICE table for this. It's initial. It's not gonna work my pens. I might get pen. Initial, change, and at equilibrium. And you start off with like kind of putting above your chemical equation here. So sometimes you'll deal with moles, sometimes you'll deal with concentration, depending on what they give you. I might do moles because it tends to work better. So place 10 moles of N2, so we got 10 moles here of N2O2 into a 2-liter container. When it decomposes, once the reaction has taken place, it is found to have 2.2 moles of N2O. So at equilibrium, we're there. Remains, calculate the molarity of all 3 substances present at equilibrium and hence the value of Kc. So we're going to do a whole bunch of things. So hey, we start with 10 moles, which means our change was 7.8. I took 10 minus 2.20. That gives me my change. Hey, if I change 7.8 moles, at the beginning I had 0 of each of those, and now I have 7.8 moles of after the change, because for every mole of this that's used, one of those is used because they both have the same coefficient of 2. But when I come over to the oxygen, for every 2 of these, I'm only going to get 1 of those. So maybe you need to set up a little stoic problem. You got 7.80 moles of N2O. You need to go to O2. So for every 2 N2O, then O2. And so you're going to get half. Maybe you can do that in your head. 0 plus 7.8 and 0 plus 3.90. That gives me at equilibrium. I need concentration, so I notice that the volume is 2 liters for all of them. So I get 2, 2, 2, and that will be my concentrations. So I can find Kc. It's products over reactants. Mystic coefficient, there's a 2 there, a 2 there. I plug in my values. Nitrogen, I have 3.90, my concentration squared. Oxygen, I have 1.95. And for the dinitrogen monoxide, I might have 1.10 squared. Take out my calculator. 9 squared times 1.95 divided by 1.10 squared. And Kc equals 24.5. These numbers seem pretty big compared to that, so it should be a number greater than 1, which it is, so that's good. And as I said, I did it with moles, but we should go ahead and show that you can do it with concentration also. So I could have started off with 5 molar, and I ended with 2.2 molar, so that'd be 1.10 molar. That means my change in concentration was 3.90 molar. Notice that it's important that our volume is not changing. So now I know my change. Those were 0 to begin with because there was no concentration. This went down. I really should have a minus sign there, sorry. And a minus sign up there. So this is going to go up by 3.9 molar. Stoichiometric ratio, for every 2 of these, there's 1 of those. So my molarity is going to go up to 1.95. And if I plug that up, that's what I plugged in, so I might get the same number. Important things to notice is that it was nice for this one that we only had the reactant to start with. There was no product, but we could have started off with some product and the process is still the same. We're going to do some examples like that.